Hey, today we will talk about generative models. So let me start by first giving you a general idea what are the generative models and how they're different from what we've done in the past, which was discriminative model. So you remember in this class, whenever we talked about classification, the pictures that you had in mind is that your classifier had a training data which consisted of some, let's say, positive and negative instances. And the job of the discriminative model was to find a separator that discriminates between these positive and negative examples. And you can easily imagine to yourself that for different clouds of these positive and negative points, you may have exactly the same separator. Even the structure of these clouds, it's totally different. So for instance, even here, I would have some different structure of positive and negative examples. Separator will be still the same. So the approach that we will be taking is actually trying to understand what is the structure of these positive and negative classes. And the way we're going to be thinking about it is saying, if I can understand in some probabilistic term the structure of positive and negative examples, maybe I can do discrimination in a different way that we've done when we're primarily looking at the separator. And we sort of start doing that when we were looking at k-means classifiers, correct? We kind of said, okay, the structure of our data would be just clusters, but in that particular case, we assume very specific type of structures that we can impose on the data, and it wasn't really probabilistic. So now we are going to move in two directions. We're going to look at much broader set of distribution that can be fitted for our data, and we're also going to add a probabilistic component to it. And today we would look at two classes of generative models which are very commonly used. The first one is called multinomials. And the second one is called Gaussians. Okay? And for both of these classes of models, we will look at them within the same lens. We're going to ask two questions here. The first question that we will ask, and this is a question that we will ask about any generative model, is the first question would be, how do we estimate this model? Because we have particular form of probability distribution, how do we fit it to our data? Okay, so the first question will be estimation question. And the second question is, when you estimated the model, how we can actually do prediction. Okay? And let me give you some very high-level idea how we can use this kind of probabilistic models for prediction, because I will start today talking actually about estimation, but later we will get to prediction. But you need to see kind of, our ultimate destination, because we do want to use these models to do prediction. So what we will do, we will fit, given our training data, the same way as we've seen before, our negative and positive points, we will fit probability distribution for the negative class and for the positive class. Now, given a new point, you can actually compute how likely is it was generated by the negative class or by the positive class. And by comparing these probabilities, we can actually induce what is the right label, which class kind of draws this point to itself. Okay? But again, before we can go to the question of prediction, we need to start by thinking, how can I find the right type of distribution to describe each class? And the first thing that I will do, I will start, as I wrote here, with one class of models which are called multinomials. Okay? So whenever we are talking about multinomials, one way example when they're very commonly used is talking about documents. Okay? So we will talk about multinomials. And in your head, you can think about texts, okay, documents, okay? And what our models, our multinomial models will do, they will generate documents. Now, whenever we were talking about supervised learning, you remember we discussed how to translate, we thought about the documents and we translated them into a vector, into a bag of words. So there was some particular mechanism that given a document, we generated a vector of fixed length. Here we are going to be thinking about it in a different way. We're going to think that our model is going to be generating documents. And some documents, which are good for this model, will have very high probability, and other documents may have low probability. Okay? So let me first show you some notation so that we can ground this discussion in a type of language that we will need to use to discuss our questions of estimation and predictions. And before I go, I want to say that, of course, you're thinking, how a probabilistic model can be generated documents. Is it going to write poems and essays? So when I'm talking about generate, it's not like generate an essay. We'll have a very simplistic definition of generate. Specifically, what we would assume that this model have fixed vocabulary, first of all. We as human also have fixed vocabulary. This is capital W, okay? And then these models would generate one word at a time. So you have this whole bag of possible words. You select one word, put it there. And then again, you go to the same bag and you select another word. And all the words that we are selecting are independent of each other. So it's a very simplistic thing because clearly we're not going to get beautiful sentences, but this is our first model that we will use. So again, the words all will come from the same vocabulary. We draw them one at a time and fully independently. Okay, so what kind of parameters do we need to have to talk about this model? So the first thing in multinomials, we need to decide how likely is to generate certain words. Because depending on the model, certain words will be more likely or less likely. So one of the parameters here would be something which is the likelihood of generating the word W given parameterization of the model. So theta means parameters of the model. So and in this case, just for ease of writing, I would write it as theta W. So theta W captures what is the likelihood of me generating certain words given all the possibilities, okay? So what kind of constraints do we need to have on the theta W to make sure that we have a valid probability distribution? So first of all, we need to make sure that each one of theta W's is bigger or equal to 0 because this is probabilities. And the second constraint is that if we look over the whole vocabulary, over the big W, we need to make sure that they all sum to 1. Okay? So this is our multinomial. And if you need another example and the text sounds to you like really weird, you can just see about dice, okay? So you're throwing dice and your dice doesn't have all the equal sides. Some sides are more likely than others, and that's exactly what our theta W would record. What is the likelihood of a particular word or number, okay? So now, given that, how can I compute the likelihood of generating certain documents? So let's say somebody gave me all these theta W's, I have them. How do I compute the likelihood of generating a document? So we would assume that we have our document, and this is capital D, and I will use it throughout this lecture, given particular thetas, okay? So if we assume that our document has n words, again, as I said earlier, every single word is generated independently. So we can just take a product from 1 to n, and then we can just write theta Wi. So we take probability of every word in our document and just multiply them all together. So now we will take the same formula and rewrite it in slightly different way. And the reason we want to do it is because in the current write-up, if we have the same word which appears multiple times in the document, we are going to separately multiply its probability. So instead we can actually refactorize it and just say we will take the probability of this word, let's say that it appears 5 times, and just make this probability in the 5th degree. So then, instead of making a product over all the words in the document, we will actually go over all the words in our vocabulary. So this is a vocabulary from above. And now we will take the probability for each word W and put it in count W in our document. So those are the two forms to write exactly the same things, but I will primarily use this representation. So now we are ready to start addressing the first questions that I wrote over there, which is a question of estimation. But before we go there, I just want to give you an example of how this model, very simple model, can be used to evaluate the likelihoods of the document. So let's take the primitive example, and I will just look at the case when my vocabulary just have 2 words, cat and dog, okay, just 2 words. And now I am going to write 2 different models that operate over this vocabulary. So this would be the first model. This is model number 1, which takes parameter theta. And I will decide that in this particular model, theta of cat, the likelihood of generate the word cat, would be 0.3. And the likelihood of the word dog in this case is kind of obvious, correct? It's going to be 0.7. As you can see, they sum to 1. They both are non-negative. And now I'm going to look at model number 2. Model number 2, and to distinguish the parameter, I just wrote theta prime. And here, let's say we want the theta prime to generate the word cat be 0.9. So you can see this model really strongly prefers cats. And then for the dog, again, because they have to sum to 1, it's going to be 0.1. Okay? So we have 2 models, and as you can expect, they will be generating different types of documents. This model would love dog style of documents, and this one is a cat model. It will prefer cats. So now assume that I give you a document D, and this particular document will have 2 cats. Okay, it has two words, cat and cat, and then it has dog. And what we can do, we can now compute the likelihood of this document being generated by the first model or by the second model. And the notation that we are going to be using here, we're going to say, what is the probability of this document D given parameter theta? And again, this is the values of these parameters. So in this case, if I just straightforwardly apply this formula, we are going to get 0.3 square multiply by 0.7. And we can compute this number. Similarly, for the second model, again, we have the document D, but now our parameters are theta prime. The cats are going to have 0.9 square multiplied by 0.1. And even though I didn't complete the whole computation, it's quite easy to see that this document will have higher probability when generated by the second model. Okay? So now we have our parameters. We have ways to compute the likelihood of the documents based on these parameters. And the question is, how can we utilize our training data to find the best parameters, correct? So again, we're coming back to supervised scenario that you've seen in the case of classifiers. We will provide our model with, let's say, positive or negative examples, and the model needs to find the best parameters that feed the data. And here we are gonna go back to our favorite principles of maximum likelihood, and we will make the assumption, this is our assumption, that the best parameters are the parameters which give the highest likelihood to our data. So you have the training data, and you're trying to find parameters for which the probability of this training data will be the highest. So in other words, what we're trying to do, we would say, we want to find the setters which maximize this expression. And again, assume that this is your training documents D over all the setters. That's what you're trying to do. And here I can rewrite it again and say max over setters. Using our previous notations, we can write probability W So it turns out, and you will see it, both in the lecture and in the exercises, that it's easier for us to do this maximization, to find the best setters, that instead of working with this expression directly, we would actually maximize the log, and we can do it, correct? So, so what we will need to do is to take the log of this expression. So let's write it down. Log Okay, and we can just do the usual thing. You remember that log of the products is actually sum of logs. So we can do sum W. And then we're taking the log of this expression, so we can write it as count W log theta W. Okay, so we will try, so now we are trying to find thetas that are gonna maximize the value of this expression. What I will do now, I will stick to the example that I had before, where I really looked at the vocabulary of only 2 symbols. Okay, we will first solve this for the case where the alphabet has just 2 symbols, and then discuss how we can solve it for general vocabulary, okay? And I know that we all love cats and dogs, but for me it would be easier to write where W would just have 2 words, exactly like in the example above, but this time I am going to be using just, instead of writing cat and dogs, I would just say the first word is 0 and another one is 1, just because it's shorter to write it, okay? So in this particular case, what's so special about this case? Because in this case, we actually just need to have a single theta. So we can write that theta 0, okay, we need a theta for 0, correct? The likelihood of generating the word 0. If we want to know the theta 1, we can just do 1 and subtract this value. So we can write theta 0 would be just my theta, and theta 1 would be 1 minus theta. Okay, so I would just have 1 parameter, and then I'm going to rewrite this formula with a single parameter. So instead, again, we are summing our vocabulary, just have 2 words. So the first part would correspond to 0. So we're going to write count 0 multiply by log theta, and this would be the parameter associated with generating the word 0, plus count 1 multiply by log of 1 minus theta. Again, in our older vocabulary, this would correspond to theta 0, and this corresponds to theta 1. Okay, so my next step is actually to find derivative of this expression with respect to theta. So we're going to take the derivative with respect to theta. And what we will get in this case would be count of the word 0 divided by theta plus count of 1 divided, and I should say 1 minus n 1 minus theta, so we can just write minus 1 minus theta. Okay, so this is our new expression, and we need to make it equal to 0 to find our desired thetas. So in this case, we can just do this computation. 1 minus theta count 0 minus theta count 1 equals 0. So if you go and do the algebra, which is pretty straightforward in this case, you can open parents and close parents, what you would get here is that the theta that we are looking for, and you see I use this estimated theta special notation, would be actually equal to something that sounds like very logical. It's going to be equal count 0 divided by count 1 plus count 0. This is kind of an obvious thing, so it looks weird. You say, okay, I have a document which have, 20 zeros and 10 ones. So what is the likelihood of observing 0 here would be 20 divided by 30. And that's exactly what this formula says. But what we've demonstrated here, that by properly defining our maximum likelihood criteria and making the estimation, we are actually getting the parameters that we are expected to get. And in some cases, for some model, you can kind of intuitively say what they should look like. In other cases, not. But this mechanism, always works. So now we are ready to start looking at the question of prediction. So again, as the same way as in case of our discriminative supervised model, we will have, our points, let's say just two classes, pluses and minuses, and using the estimation techniques that I just described to you earlier, we can actually induce the probability distribution. Find thetas, correct? Find thetas for this class. I would denote them as theta plus, and also find thetas, find the parameters for this class in such a way that they will give the highest likelihood to the points, for instance, on the plus side. Okay, so we'll use this data to induce those theta pluses and use this data to get theta minuses. So now the question is, if I give you a new document, how do you know to which class it belongs, correct? So one way to think about it is to say, okay, I have my document and I could look at the likelihood that this document was generated by plus side, and I could look at the likelihood that this document is generated by the minus class and look at its log. You can ask me why are you looking at the log, you will see later. But the point is, intuitively speaking, we would want to say that the document will be assigned to the class which gives to it the higher likelihood, correct? And for now, I will make one assumption, which I'm going to break later. But for now, let's make an assumption that the likelihood of a document to be in the minus plus or the prior likelihood of the minus class or the plus class are exactly the same, okay? So in this particular case, we are going to be looking at this log, and we would say that if it is bigger or equal to 0, then we are going to return plus, and if it is smaller than 0, we are going to return the minus. So this type of distributions are called class conditional distributions, so that you just know this is class conditional distribution. Okay, so let's just look more closely. I'm going to just open up this expression and massage it in a different way, and eventually I will bring it to you to the form that you already seen in the past. But let's just start. So again, we have here log of this ratio. We can just write it as log of one expression minus log of another expression. Okay, so as you already remember that we can actually express this probability by looking over the words that are in a vocabulary. So I'm going to do it here, log, and then we're going to take a product over all the words in the vocabulary. Theta W, count W. And here I am adding theta plus, because this is the theta of the plus class, correct? This is a derivation for this expression, and I will write very similar expression for the negative class. Okay, so now what we can do, we can continue to do some manipulation, and again we remember that log of the product, it's a sum of logs. That's what we're going to do next, and I'm going to write sum over all the w's. Then log of this expression would be actually count w multiply by log theta w plus, and very similar expression for the negative class. Okay. So I will do my almost last rearrangement here, and I'm going to group these two guys together, because you can see that this part and this part is shared. So we're going to do sum W count W, okay? And then here we're going to write log plus W divided by log minus W, okay? And the last thing that I am going to do, this is truly the last thing, I am going to just introduce for you a new notation, okay? So instead of writing this big expression, I am going to just call it like some theta hat W. When we remember the theta hat W is just this log of a ratio. So I'm just rewriting it here, and you would immediately see why it is a good idea. Count W multiply by some theta hat W. Okay? So if you are now looking at this expression, so remember we started here, and then what I got at the end. So at this point, looking at this expression, which we derived, or looking through the generative view on classification, actually what we got here should remind you a linear classifier that goes through origin with respect to this parameter theta hat W. So despite the fact that we went in a very different way, what we got with our generative model, we still get a linear classifier, just get there in a different way, okay? So now what I want to do, I told you, one of the limiting assumptions here is that I assume that the likelihood, of being plus or being minus, it's exactly the same. So sometimes we may have some prior knowledge and we want to enable our models to take advantage of it. So I will demonstrate to you how we can break this assumption and look at a more general case, okay? So the first thing that I would like to do is to remind you, Bayesian rule, so that we are all at the same page. Okay, so we can write here this is just a Bayesian rule. There is nothing very special about it. So now let's see what we can get when we actually are applying this Bayesian rule to our computation. So again, my goal here is to compute the likelihood that my document is going to get labeled plus, for instance. So I'm saying, what is the likelihood that given document D, I will give to it label plus, okay? That I will give to it label plus. So what I will do, I will rewrite this expression. I will rewrite it as theta plus D multiply divided by PW. So there is a bit clash of notation. Let me explain what I mean, because we're kind of using slightly different notation to mean the same thing. So here I'm saying, what is the likelihood that I'm going to assign to document D its label Y, which is plus? So I rewrite it based on this rule, and we are now looking at two parts. The first part is given that this is a document which has label plus, in this case that got the parameter C plus, we're going to generate the D. Then we're looking at the likelihood of the label Y to be plus. I could have wrote the likelihood of theta plus, but I just want to be consistent with notes. And here we are dividing it by the likelihood of the documents, okay? So first of all, let me introduce you some notations that you're going to see later on. So this part is typically called prior, okay? This is called prior. It's just the likelihood of a certain class to be like, the likelihood that you're going to, a document will be spam. Even before we are looking at the document, each one of us have different ratio of spams in their email. So this is even without looking at the document, we can say what is the ratio of spams we expect to see. This one is called posterior, because we are looking now at the likelihood of the class when we already seen the document, and this one called is the likelihood, okay? So now what I will do, I will actually look at this expression in more details and again translated it to a very similar form, connect it again to the linear classification, okay? So what we can do here, we can again do the same story. We're going to take the log, and we're going to take the log of y belongs to the plus class divided by y belongs to the minus plus, okay? In other words, we're looking at the log of p d plus multiply by y plus divided by p d minus multiply by y minus. And you can see that probability of the document disappeared here because we just can cancel it away. Okay? So now again, because of the log, I'm going to separate it to two subparts. This subpart we already seen in the past, correct? So I want to separate this portion from this portion. Okay? So I'm going to write log P d sigma plus divided by P d sigma minus plus log P okay. So we know already the value of these expressions. That's exactly what we already computed here. So I'm just going to take it from here and rewrite it here. So I am getting now sum over all the w's of count w. And then you remember there was a squiggly theta w plus. Now I have this expression. And the same way, just for simplicity, to make the notation really crisp, I make this substitution, you remember. I'm going to make the same substitution and just call this whole expression. I will denote it as theta hat 0. So now what we actually see here, that we translated it again to a linear classifier, but in contrast to the previous case when we had linear classifier that went through origin, now we have linear classifier with an offset, and the offset itself would be actually guided by our priors, which will drive the location of the separator. So what we've seen here, that in this model we can very easily incorporate our prior knowledge about the likelihood of certain classes. And at the end what we got, that even though we're talking about generative models and we're using a different mechanism on some ways of estimating the parameters of this multinomial, at the end we actually are getting the same linear separators that we see in our discriminative modeling. So, and before we move and we're kind of done with the multinomials, I just want to make one clarification point about the notations, okay? Because you remember the setters are defined over the alphabet. So in this case, when we are thinking about like the setters for the positive class and negative class, think about our cat and dog examples. That when we did the estimation, maybe for this class, we get theta cat to be 0.7 and theta dog to be 0.3. And this will be the setters for the negative class. And maybe, given our estimation procedures that we've done, setters for the positive class for the cat would be maybe 0.5. And again, for dogs, it's going to be also 0.5. So what you will do whenever we are computing now, I give you a new document, which maybe only have cats in it or something. We will have a mechanism that would estimate for us the likelihood of it belonging to certain class and getting the label plus or the label minus. So here again, we will have multiple thetas because we will have a big vocabulary, more than 2 many times, that correspond to the negative class, and different kind of parameters of theta for the positive class. And the relation between them would determine how this expression look like. Okay, so now we finished talking about multinomials. And again, just to recap, when we talk about multinomials, I described to you how to estimate thetas, and we discussed how we can use it to actually, these multinomials, to make predictions. Now we are going to switch gears and look at a different example. We will start talking about Gaussians. So before we were talking about the words, now we are going to go to vectors and RD and find distribution that is a very natural fit for describing this data. So now we will start talking about Gaussians. And it is appropriate to use Gaussians when we are looking at vectors in RD. And again, D is a dimensionality of the space. And Gaussian is maybe the most of the vanilla distribution, where we are looking at a cloud of points. And the way we are going to describe these points is by two parameters. the first parameter will be kind of where is the center of this cloud, and we would call the center, the mean, as mu, okay? And then we will also have another parameter, which is called sigma square, which would look at how dispersed is this cloud. Is it really tight and very close to the center, or the points can be dispersed? Now, you can be thinking to yourself, maybe points in my particular examples are not really nicely described as a sphere. Maybe there are actually multiple clouds. But in this case, we're going to make an assumption that the only way we can describe it, if we decided to use Gaussians, is actually to assume that there is some mean for all these different clouds, and there is certain sigma squares that will tell you how dispersed they are. And this is actually an important modeling point related to generative models. You always are making assumptions, and these models that you are selecting, when you have multiple choices, you need to decide which class of models is appropriate to your data. So in this particular case, again, if there are even many more clouds, for now we will make an assumption that we will characterize them by these two parameters. And typically when people think about Gaussians, in their head they're thinking about the sphere. Again, the center here would be mu, and the radius of this sphere would be the sigma. Farther away you go from this mu, the lower is the likelihood that the point was generated by this Gaussian, and it doesn't matter to which direction do you go. So the mu, the meaning of mu would be just an average of all these points, and sigma square is just a square of the average distance of x's from the mu, okay? So now we kind of discussed about what this model is roughly speaking captures, and we need to write the probabilities to talk about the parameters of this probability distribution. And as we can see here, there are just two of them. So we can write for any point x, given the parameters mu and sigma squared, we can write the likelihood of x to be generated by these Gaussians. So in this case, it's going to be 1 divided by sigma square d divided by 2. So this is just a normalization constant, and you can see the d is the dimension. And then here we have exponent minus 1 divided by 2 sigma square is x minus mu squared. Okay? This is the likelihood of a particular point being generated by the Gaussian, and you can see that if we select different mu's and different sigmas, the same point may get different likelihoods. So now imagine to yourself you are actually given some training set, and we want to find, as what we've done before when we were talking about the question of estimation, how can I find the best mu and sigma square that will give the highest likelihood to my training data? Again, in this case, the training data will be just vectors x, t, and t would go from 1 to n, because we have n points in our training data. Again, since all the points are independent, whenever we are thinking about the likelihood of all these points being generated by our specific Gaussian, we just need to multiply the likelihood of every training point to be generated by the Gaussian. So we're going to write the product of t going from 1 to n, because we have n points, and then likelihood for xt mu sigma squared. And I can continue and just copy this expression here instead of x writing xt. So what do we want to do for the hour estimation task? For our estimation task, for given set of points xt, we want to find the sigma and the mu, which gives us the highest likelihood. And the same way as we've done it before when we were talking about multinomial, instead of directly looking at this expression, we're going to log it because it will be easier for us to work with it. Okay, so let's do that. So we are looking at log of this expression. And what I will do, just to reduce the amount of copying I have to do, instead of writing this probability, I'm actually going to write this whole expression above. Okay? So log p, again, instead of this, we're writing that guy. Okay, and the log 1. So what we can do, as we've already seen many times today, when we're looking at log of the product, it's actually going to be the sum of logs, correct? So we're going to write now sum from, sum from t to n. And here we are going to do log of this whole expression. So you can see that, again, the log of this whole expression, there are two parts to this expression. So again, could have rewritten it, but there is no point. We can separately take this log and sum them up. So that's what I'm going to write. So log of the first part plus sum into 1 log exponent, and then this whole expression minus 1 to sigma xt minus mu squared. Okay, so now we can actually do some log computations. So here we're again doing our sum from t from 1 to n, and then we're going to get d divided by 2 minus d divided by 2 log 2 sigma square. And similarly, we can do the same computation here. And we are going to get minus 2 sigma square minus mu squared. Okay, so the first thing to notice is that actually here we are not having any dependence on the t. We're just going to t times sum up this expression, sorry, not t, n times sum up this expression. So instead of writing the sum, we can just multiply it by n. So here we're going to get minus n d divided by 2, and I would keep this log as it is. Here again, log and exponent disappears, and we're just going to have sum of this expression, but because this part doesn't depend on xt, I can just take it out. So we're going to write minus 2 sigma square sum from t to 1 xt minus mu squared. Okay? So Now we have this expression, and we are trying to find sigma and mu that will give the highest the highest value of this expression. And we are going to do exactly the same things that we've done in the past. Let's call this expression as capital L. So in this case, we are going to take our expression dl and differentiate it with respect to mu and make it equal to 0. And similarly, we are going to do the same with respect to our sigma, make it equal to 0. And from there, we can compute the mu and the sigma. And that's actually will be your homework to complete this computation. And what you will get here would be, again, something extremely intuitive. That we will find out that the mu that we are going to get here, for instance, this mu would be just the mean of all the observed points. It's going to be 1 divided by n and sum of all the points. And similarly, you would find that sigma square is what we expect it to be, which is the average variance of the points from the mu. So you would go exactly through the same machinery as we went through the multinomials to see that those are the same mechanisms that are used to do this computation. So in our next lecture, we're going to continue with the Gaussians, but we are going to slightly make it slightly more interesting. And instead of telling you that we are just going to always assume we have one mean and one variance, we would actually assume that there can be many different means and there can be many different clouds. We will see how this expansion is done and how we can estimate it.